This video explains the current started VCO working principle. It is a particular kind of voltage-controlled oscillator widely used in phase-locked loop for the low chip area and the good tunable frequency range. A voltage-controlled oscillator or VCO is an electronic oscillator designed for producing oscillation frequency by a controlled input voltage. The frequency of oscillation is varied by the applied controlled voltage. An ideal VCO is a circuit whose the output frequency is a linear function of its control voltage, but we will see this is not the case for the current started VCO. VCOs are a crucial building block for phase-locked loops. Current started VCO is a type of VCO based on ring oscillator, with extra CMOS acting as current source for the inverters. A ring oscillator is a cascade of another numbers of inverters with a feedback. The first feature of the ring oscillator is the logical instability. If we put a high value in the input, we have a low value at the end of the cascade, which is fed back in the input by the feedback, putting the input to low value, which in turn produces a high value at the end of the cascade, and so on. There is a combinatorial contradiction and the circuit is unstable. The second feature of the ring oscillator is the delay introduced by the inverters, which is defined by the capacitive load given by the input and output of each stage, and it is proportional to C oxide and to the length and section of the channel of the P and N MOS. This means that the output of the inverter will take some time to update the value after the input changes, so the circuit can hold the logical contradiction for a period of time. The delay of each inverter is calculated as the time needed to charge and discharge the capacitor up and down. But let's see the inverter delay. If we give a pulse of 5 volt to the input of the inverter, the NMOS M1 switches on and the PMOS M2 switches off, so the output voltage goes to 0. The opposite happens when from 5 volt the input goes to 0, so in this case the output is connected with the 5 volt of the power supply. In this diagram, we see the output voltage as function of the input voltage. We see three regions. In the first and in the third, we have one transistor on and one off. But in the second region, we have the transition of state and both transistors are in on, in saturation mode. We can say that the switching point is when the voltage of the input is equal to the voltage of the output. We call it VSP, and in our example is VDD half, so 2.5 volts. So we define two times. The first time starts when the high pulse arrives in input till the moment the output and the input have the same value VSP, so till the switching point. This is the time for the output transition from high to low. The second time starts when the input pulse goes to 0 till the moment the output and the input have the same value VSP, so this is the time for the output transition from low to high. These two times are different because the resistance of the PMOS is bigger than that of the NMOS because the holes have less mobility than the electrons. So the NMOS is faster than the PMOS. The precise formula is this, and you can see the transition time depends on the building factor of the P and N MOS as C oxide, the length of the channel, and of course on VDD, the power supply, which is in the numerator but also in the denominator we have the square of VDD. So as higher is VDD, as shorter is the time and faster is the transition. So now that we have understood the inverter delay, we can define the oscillation period of the ring oscillator, and this is simply the time the output of an inverter goes from a logic 1 to a logic 0, plus the time it comes back to a logic 1, times the number of inverter. So the period is the time high-low, plus the time low-high, times n. The frequency is the inverse of the period, and as many inverters we have, as less is the frequency. Now we come back to the whole circuit. We recognize the ring oscillator composed by odd numbers of inverters plus the feedback, and now we see the purpose of the other transistors. You see that M5, M6 and M1, M4 are in a current mirror configuration, so the current created by applying A voltage Vin in the input of M5 is mirrored in all the inverters. These currents will charge and discharge the total capacitance, so now the oscillation period doesn't depend only on VDD and on the building parameters of the CMOS technology, but it depends also on this mirrored current, which in turn depends on the input voltage of the VCO, Vin VCO. This means that we can adjust and set the oscillation frequency by setting the voltage applied on the input of the circuit, so on the input of the transistor M5. If you need an explanation about current mirror, I leave a link in the description. Let's calculate the oscillation frequency as function of the current, so let's focus between two stages of inverters. The total period is given by the time it takes to charge the total capacitance from 0 to the switching point VSP with a constant current ID4 plus the time it takes to discharge the total capacitance from VDD to the switching point VSP with a constant current ID1. We want to set the center frequency, which is the working frequency, so that the input voltage V in VCO is equal to VDD half and ID4 is equal to ID1. Then the total period is C tot times VDD divided by the current ID, and the frequency for an n stages with n odd number is this. You see, the frequency of oscillation depends on the current ID, which is modulated by the voltage in input, so the inverters are limited in current by the current mirror, and that's why we call this circuit current-starved VCO. So by varying V in VCO, we vary the mirrored current ID and we vary the oscillation frequency. The minimum oscillation frequency is 0 for V less than the threshold voltage of M5, and the maximum frequency is determined by finding ID when V in VCO is equal VDD, the maximum voltage. In this way, we have the range of frequency of our VCO. Now remember that when the MOSFET is in saturation, the current ID is related to the voltage between gate and source, VGS, by this quadratic relation. This means that the input voltage V in VCO of our circuit is proportional to the square root of the frequency. So the relation between the input voltage and the oscillation frequency is not linear as it is in the ideal VCO, but it is this. But there are ways for linearizing this relation. To make the current in a MOSFET linearly related to the VCO input voltage, consider this circuit. The width of M5R is made wide so that its V gate source is always approximately V threshold. In this way, the increasing of the input voltage drops on the resistor R, linearizing the relation between V in and the current ID. Note that the current ID in M6R is mirrored over to M6 and M5 to control the current used in the current-starved VCO. So now the relation between the input voltage and the frequency becomes similar to this one, which is linear. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.